Okay, so let's start chapter 9. Chapter 9 is all about substitution and elimination reactions. One of the molecules that was made through substitution and elimination reactions is the famous DDT, which is a pesticide that was once advertised as being healthy for all persons and is now banned for use in the United States. All right, so chapter 9, we're starting our types of reactivity as group 2 reactivity. We're going to cover the reactions of alkyl halides, alcohols, epoxides, sulfonyl esters, quaternary ammonium salts, and thioethers in the next couple of chapters while we're in group 2 and type of reactions. So in terms of making alkyl halides, that's covered in chapter 11. Reactions of alkyl halides, many different nucleophiles replace halogen atoms, and so that is going to be covered largely in this chapter as well, chapter 9. So we have the generic alkyl halide is Rx. Our alcohol here, this is our ether group. It's a carbon bonded to single bond oxygen, single bond carbon. Epoxides, you've already seen. Sulfonyl esters, these are going to be used as molecules. We can make them, but they're also primarily used as protecting and leaving groups. So we can make an alcohol into a sulfonyl ester. And then this sulfur is very electrophilic, and the carbon that the sulfonyl ester is bonded to is also very electrophilic because electron density is being drawn away from the carbon. Okay, thioethers, these are molecules that have sulfur-carbon bonds, more than one bond from sulfur to carbon, and quaternary ammonium salts, which we use mainly in a Hofmann elimination reaction towards the end of the chapter. All right, so beginning. The compounds in group 2 are going to be electrophiles. So we're going to discuss our R groups being electrophiles. And they are bonded to, ideally, group 2 compounds in group 2 are electrophiles, and that they are electrophiles resulting as the result of a partial positive bond or a polar bond. And especially for alkyl halides with X is going to be a good leaving group. So there's going to be an electronegative atom and an electron withdrawing group. All of the compounds in group 2 have electron withdrawing atom or group that is attached to an sp3 carbon, and this causes the sp3 carbon to be electrophilic. So we're going to be covering reactions where we have a nucleophile that is reacting at this electrophilic carbon, and when carbon makes a new bond, it has to lose a bond that is already present, and so we have a good leaving group that is attached to the carbon, and the leaving group is the group that causes the carbon to be electrophilic, or the electronegative atom that is part of the polar bond. Okay, so beginning with group 2 compounds that are electrophiles, our favorite group 2 compound that is an electrophile that we're going to focus on a lot in these next few chapters are going to be alkyl halides. So we have here, for example, an alkyl halide with X, the leaving group, and Y, a nucleophile. And we're in this chapter, specifically in chapter 9, we're going to cover two main types of reactions. Substitution reactions. The electronegative group is replaced by another group, and in terms of the electronegative group, they're referring to X. So they're referring to the X in yellow. And in a substitution reaction, X is replaced by Y, our nucleophile. In an elimination reaction, the electronegative group is eliminated along with a hydrogen. So X leaves and a nucleophile removes the hydrogen from the group, and in the process we make an alkene. So for example, okay, I will try that again. Okay, let's try that again. It's not working. Okay, so for example, we have our RCH2CH2X, and the carbon adjacent to the carbon bonded to the halide in an elimination reaction, the nucleophile removes that hydrogen on the adjacent carbon. The bonding electrons for the hydrogen form a pi bond between the two carbons, the CH2CH2, and X leaves to form an anion. And so that's an elimination reaction. It's a method to form alkenes. All right, our first group, first of the families in group 2, we're going to cover alkyl halides. Alkyl halides have relatively good leaving groups, except for fluoride. It's not usually a leaving group. It's actually a relatively bad leaving group in most circumstances because it is not the conjugate base of a strong acid. It's the conjugate base of a weak acid. And so its bonds are stronger. Substitution reactions. So we're going to start with substitution reactions. We'll start with one type and then we'll move on to the next. The first type of substitution reaction we're going to cover is going to focus on primary and secondary alkyl halides in substitution with that type of alkyl halide. So you can see in a substitution reaction, we take X, which in this case is bromine, and replace it with Y, which in this case is hydroxide, and we're making, so we're changing, in this case, an alkyl halide to an alcohol. And I can show you the mechanism. So we have our alkyl halide, and our Y, or hydroxide, is going to act as our nucleophile. The nucleophile bonds to our electrophile, the carbon atom, and the bond between carbon and bromine breaks. So we could show in the transition state that because the bond forming and the bond breaking occur at the same time, the hydroxide is actually bonding to the carbon exactly 180 degrees apart from the bond between carbon and bromine that is breaking. So we have bond forming in red and bond breaking in red. What is the mechanism of reaction? Remember when we were talking about mechanisms in Gen Chem 2? We referred to the overall mechanism as being several steps, and then you could usually eliminate all intermediate products to show just the reactant and the final product in our reaction expressions. In the kinetics of a reaction, the factors that affect the rate of the reaction help determine the mechanism. So we like to do a lot of work with mechanisms in organic chemistry, and we're going to first look at the rate of the alkyl halide and the nucleophile. So we are actually going to look at two types of substitution. One is called substitution nucleophilic bimolecular, and bimolecular means that in the rate law, both the alkyl halide and the nucleophile affect the rate. And so they are second order overall with first order with respect to the alkyl halide and first order with respect to the nucleophile. So when we add the two exponents together, we get second order overall. If we double the alkyl halide, we double the rate. If we double the nucleophile, we double the rate. If we double both, we quadruple the rate. Okay, so remembering rate law, the rate can be written as the rate constant times the concentration of alkyl halide and the concentration of nucleophile. And the rate law tells us what molecules are involved in the transition state of the rate limiting step, depending on the order. So this is where we had, if you remember the more generic form from Gen Chem, we had rate is the rate constant times A to the power of A and B to the power of B, where A and B are the order. So if A and B are both 1, then the overall order is 2. And it's first order with respect to A and first order with respect to B. For an SN2 reaction, the rate law is going to be that we are first order with respect to the alkyl halide and first order with respect to the nucleophile. So both the alkyl halide and the nucleophile affect the rate of reaction. And they are both involved in the rate limiting step of the reaction. All right, so let's start. A substitution reaction that is bimolecular, second order. So the 2 here means it's a second order reaction. And that actually, a lot of people get confused because later on we're going to look at a reaction that is first order. And the second order reaction occurs in one step, and the first order reaction occurs over several steps. So the number attached to the SN is not referring to how many steps in the mechanism of the reaction. It's referring to how many reactants affect the rate of the reaction. Okay? So I think that might be an important note to make. So number of reactants that affect rate of reaction. All right, so now let's look at the relative rates of an SN2 reaction in terms of the alkyl halide. So here we go. Relative reactivities of alkyl halides and SN2. A methyl halide is the most reactive, followed by primary alkyl halide, a secondary alkyl halide, and then a tertiary alkyl halide is too unreactive to undergo an SN2. So tertiary alkyl halides will not undergo SN2. Methyl halides, primary alkyl halides, and sometimes secondary alkyl halides will undergo SN2, but tertiary alkyl halides will never undergo SN2 reactions. Okay? Inverted configuration. This is, so in an SN2 reaction, because the bond breaking and the bond forming occur simultaneously, the product ends up with an inverted configuration compared to the reactant. So if the reactant is S2-bromobutane and the product will be R2-butanol. So we invert configuration from S to R between reactant and product when we have an SN2 reaction. So our alkyl halide is bonding to the 180 degrees away from the bond to the electronegative atom of the alkyl halide. And because of that, we call it a backside attack. And I think it drew the intermediate of this earlier. Here we have recall the transition state that I drew for you. This results in an inverted configuration. Before the hydroxide bonds, we're in tetrahedral formation, and the carbon atoms' hydrogens are in a pyramid on the left side where the hydroxide bonds. When hydroxide comes in to make a bond and bromine is leaving, then in the transition state, the carbon is trigonal planar. After the new bond is formed, then these hydrogens fold towards the bromide because bromide is no longer there and it doesn't require the space, and the hydroxide atom needs its space. Okay, so you can see here, and you should build these molecules to see what is happening. All right, summary of experimental evidence for the mechanism of an SN2 reaction. Both the alkyl halide and the nucleophile are in the transition state of the rate-limiting step. The relative rate increases, yes. It takes longer for the reaction to occur as we change the alkyl halide substitution. So we are faster for primary alkyl halides and slow for secondary alkyl halides and not occurring for tertiary alkyl halides. And then the configuration of the product is inverted compared to the configuration of the reactant of a chiral alkyl halide. And so these are all evidence that are supporting the mechanism we're going to propose for an SN2 reaction. So here's our mechanism. Hydroxide ion attacking the methyl group and bromide ion, bromide leaving the carbon, so that the OH bond is forming at the same time as the CBr bond is forming. And we achieve a methanol. This is called a backside attack. Why backside attack? So this has to do with our favorite orbital expressions, LUMO and HOMO. Highest occupied molecular orbital and lowest unoccupied molecular orbital. So remember that for a new bond to form, we must have in-phase bonding overlap. And when we have a new bond forming, the electrophile is accepting electrons into its lowest unoccupied molecular orbital. It cannot accept electrons except into the lowest unoccupied molecular orbital. The other orbitals are occupied. And when the nucleophile is donating electrons, it's donating electrons from its highest occupied molecular orbital. So the nucleophile only has in-phase interaction with the electrophile, LUMO, when the nucleophile has a backside attack of the LUMO of the electrophile. And so this results in the bond is occurring at the sigma anti-bonding molecular orbital, and when the CBr bond breaks, then those electrons leave, then the sigma bonding molecular orbital is empty of electrons, and the electrons that entered into the LUMO of the carbon then drop down in energy. If we were to have front side attack, then we would have repulsion of the nucleophile's electrons with the bromide atom that is in the way, and there is out of phase interaction with the electrophile, so that the nucleophile and the electrophile can't form a bond when the orbitals are out of phase. Why bimolecular? So these are just interesting facts, okay? We're not asking you to memorize why this happens. What I want you to memorize is that it does that there is a backside attack and that causes inversion of configuration between product and reactant. So that if you have a reactant that is R, the product will be S, and if you have a reactant that is S, the product will be R. Why bimolecular? The CBr bond breaks as the CO bond forms. So the OH is always entering 180 degrees away from the bromine. And that's one of the things that's going to help you to remember that it's a backside attack. The transition state contains both the alkyl halide and the nucleophile. I try to think of backside attack as being necessary because if the bromide is present, then how can the hydroxide possibly form a bond at the same position? It has to form a bond at a different position than the bromide is bonded to, and it's usually 100, and for SN2, it's 180 degrees away from where the CBr bond exists. Okay, why do methyl halides react fastest and tertiary the slowest? The reason is steric hindrance, increasing steric hindrance. So if you look at the maps shown at the top, we have methyl, which is the fastest by SN2 attack. We have our electronegative oxygen coming in to make a bond to the back of the carbon. And in order to be able to make a bond to the back of the carbon, you have to have access. You have to be able to actually see that that carbon is there, okay? For a primary alkyl halide, now we have a methyl group at the top, and so we have less access to the carbon atom that is bonded to, that the hydroxide is going to bond to. When you get into a secondary carbon, you can see here this red line expressing that there's even less of a window to come in and bond to the secondary alkyl halide carbon. And when you get to a tertiary carbon, the methyl groups are so in the way that you cannot even, there is no exposure of the carbon atom that the hydroxide would be bonding to. And remember what steric hindrance is. It's repulsion of an atom because of proximity, because of the outermost part of the atom is the electron cloud. And so this methyl group is repelling the hydroxide ion, but it can still bond to the carbon because there's enough of that positive carbon exposed. And the secondary alkyl halide is going to react more slowly because of the repulsion of two methyl groups instead of just one. And then the tertiary alkyl halide can't occur at all because of the number of atoms present repelling the hydroxide atom away from the partially positive carbon. So we have increasing steric hindrance as we go from methyl to tertiary and decreasing rate of reaction. Why the configuration of the product is inverted. So here we have a secondary alkyl halide that reacts with hydroxide, and we can't think of the hydroxide is replacing bromide, but it is replacing it from the other side. And so what we do is that the methyl and the ethyl are still in the same plane, but the hydroxide and the hydrogen are on the other side. So we get 180 degrees, and you can see some people call this turning the umbrella inside out. So if you think of these atoms as forming an umbrella, and then nucleophile comes in and makes a bond, in the transition state, the atom adopts this planar geometry as the bond is forming and the other bond is breaking. And so the umbrella becomes completely flat at the transition state and then is turned inside out in the product. All right. Steric hindrance is going to decrease the rate, and what is going to be changed is the activation energy. So it's going to require more energy to enter the transition state for the final product. All right, because the more crowded the transition state is, the higher energy the transition state is, and the higher the energy of the transition state, the slower the reaction. And just remembering that SN2 refers to both reactants having an effect on the rate, but it is a one-step reaction. So you can see from the graph that this is a one-step reaction. There is no intermediate cation or other molecule. Okay, so 1-bromo-2,2-dimethyl-propane is a primary carbon. We have a primary alkyl halide because this carbon here is a primary carbon. It has only one mother bond to carbon. If it's a primary carbon, why does it react very slowly? Because there is still steric hindrance. The primary carbons can be sterically hindered if they are bonded to quaternary or tertiary carbons. So with SN2 with steric hindrance can occur, but it will be very slow. Next, we'll talk about the weakest base being the best leaving group. So we know we talked about the alkyl halide itself, the carbon atom, the substitution of the carbon atom, and how that affects the rate of reaction. All right, so the carbon of the alkyl halide that is bonded to the halide and its substitution and how that affects the rate of reaction. That's what we've just covered. The next thing that we're going to cover is how does the alkyl halide affect the rate of the reaction? So now, spelling. How does the X affect rate of reaction? So we know how carbon affects the rate of reaction. Substitution of carbon. I don't like that. Substitution of carbon. Of CX, how this substitution of the carbon of CX affects the rate of reaction. And now we need to know how does X, how does X of CX affect rate of reaction? Okay. Okay, so how does the second thing that we're going to look at now that we've covered how C affects the rate of reaction, how does the X of the CX affect the rate of reaction? but let's wait for the next video.